Alright, so now we want to explore z-scores a little further by seeing histogram and z-scores, how they can be related, right? Excuse me. So we're going to look at, so this is how data analysis, multiple representations. So we're going to look at multiple representations of our data. So here we have the grades in the class are 40, 60, 65, 72, 72, 75, 78, 78, 78, 83, and so forth. We're told the mean x bar is 75.6. The standard deviation is 14.1. And here it's just saying we're going to continue working with z-scores and explore how they relate to data distributions and histograms, right? Like I said. So one important fact we want to recall is the formula for z-score, right? So remember that's taking our x value minus the mean divided by the standard deviation, and this tells us how many standard deviations away is that data point from the mean, right? Which is a ratio, right? So in number 1, it says in the following dot plot showing the distribution of grades, put tick marks on the x-axis from 40 to 100 every 5 units to indicate the mean with the tick mark, right? So I just want to take a minute to explore what this dot plot represents, right? So for example, if we look at the score 60, there's only one score at 60, right? So there's a dot plot at 60. Where if we look at the score 78, there are 3, right? So this goes up to 3, right? So there's a dot at every for every data point on here, right? So this is another way to show a similar characteristic of the data like a histogram, but showing it using dots, right? Right, so what we were asked to do is to put tick marks every 5 units, right? So like here, this would be 45, right? 55, 65, 75, 85, and 95, right? So that's what we're asked to do. So now it says the x value would have a z-score, what x value would have a z-score of +1, -1, -2, and 0. And we're asked to put a tick mark on the x-axis for each of these values, right? So we have a chart, and we just need to calculate those. So we're going to use the formula z equals x minus x bar all over the standard deviation, right? So if I want a z-score of 1, right, we would have 1 equals, and then we don't know the x value, so that's x, and then we would subtract off the standard deviation, which we were told up here, 14.1. We also need to know the mean, 75.6, right? So I'll just make note of that here. Was 75.6. Right? So we take x minus the mean, which is 75.6, and then divide by the standard deviation, which is 14.1. Right, so we need to solve for x. So if I multiply both sides by 14.1, I would have 14.1 equals x minus 75.6. Then I can add 75.6 to both sides. And I'm left with, this is a 7, right? I'm left with 89.7 equals x, right? So 89.7 would go here. Now one thing that would be helpful is if we could take this equation, z equals x minus x bar over standard deviation, and solve for x, right? That could make our calculation faster, right? So if I multiply both sides by the standard deviation, right, then I would get z times the standard deviation equals x minus x bar, and then I need to add x bar to both sides. I'm left with z times the standard deviation plus x bar equals x. Right, so I could use this equation in order to quickly calculate. So my standard deviation is 14.1 and my x bar is 75.6. So if I plug these in, I can even get a better equation. So x equals z times 14.1 plus x bar, which is 75.6. Right, so now we have a linear equation that we can plug in z values in to get x. Right, so in other words, I'm wanting this to be my input and this to be my output, right, in this function, this table. So that way I can just input something and calculate the output very quickly, right? So we just need to plug in -1 in for z, -2 in for z, 0 in for z, and simplify. So plugging 0 in for z would be easy, right? Because what would happen is this term just becomes 0, right? Because 0 times 14.1 is 0, so we would have 0 plus 75.6, so that would be just 75.6. Right? So we could calculate the other two. Right? So if I take -1 times my standard deviation of 14.1 and add 75.6, 75.6. Right, this will give me 61.5. Right. And then I can simplify if I have a standard deviation or a z-score of -2, right? So input that. So -2 times 14.1 plus 75.6, I get 47.4. Right? So we have all of those. And then we want to put a tick mark on the x-axis for each of these values, right? So I'll do this in let's do it in red, right? So 79.6 would be, or excuse me, 75.6 would be about here. So I got that one. Next one, 47.4. So I guess I'm going backwards. All right, so this would be 47.4, roughly. Then we have 61.5, so that would be somewhere around here. And then 89.7 be somewhere about here. Right. So 75.6, this refers to a z-score of 0. This corresponds to a z-score of -1. This corresponds to a z-score of -2, right? This corresponds to a z-score of, this would be +1, right? 89, yep, +1. So this can be thought of as my z-axis. Right, z-axis. So another thing that you want to note, let me do this in, I'll do this in black, is that here's the mean, right, x bar. The distance between here and here is 14.1, right, which is the standard deviation. The distance between here and here is also 14.1. The distance between here and here is 14.1. And then if we had a z-score of 2, the distance between that would be 14.1, right? So the distance between any whole z-score will be the standard deviation, right? That's what the meaning of that is. So it says we will treat the 0.5 axis so as the z-score axis using the dot plot for number 1, put tick marks for the z values. So we already did that, right? We already did number 3. So number 4, we're still using this data. We want to be able to compute the IQ scores and the SAT scores for the data values in table from question 2, right? So you're told here that the point here is that what matters is not the raw scores or data value, but only the relationship of the data values to the center mean and the spread, standard deviation, right? So any of the following scores accurately represent the data set could be used as a scale on the x-axis, right? So in other words, I could replace the x-axis with replace any of the values in the same column and still have the same type of information presented in the graph, right? Still accurately. So for +1, right, my z-score was 89.7, right? So 89.7 would go here, right? So I'm just pulling that off of page 33, right? The first page of this that we were given from question 2. So the -2, the x value that we had there was 61.5. For -2, the x value was 47.4. And for 0, the x value was 75.6, right? So that's our raw data, raw score. So then we want to convert this into IQ and SAT scores, right? So the IQ equation is 100 plus 15 times z, right? So we're just going to plug values in the z-score to get the IQ score. So for like this IQ score, we would plug in 89.7. Excuse me, plug in 1, right? Because we're not plugging in the x value, we're plugging in the z-score. Right, so it'll be 100 plus 15 plus 1, right? And this would give me 115, right? So we could also calculate the SAT score. So the SAT is equal to 500 plus 100 times z, right? So this would be 500 plus 100 times 1, so we would get 600 here, right? So in other words, what's listed here, this is the mean, right? And then what's being multiplied by the z-score, right? This is the standard deviation, right? If you remember right from the last worksheet, right? We have those values given to us, right? So rather than calculating the rest of these all the way, I'll leave you to calculate those, and I'm just going to fill these in. So this would be 85, this would be 70, this would be 100, right? And then this would be 400, 300, and then 500, right? So you can double check those. So now we're going to draw a histogram of the data, right? So we're still working with the same data set. We want to draw a histogram. So it says first you must choose intervals or bends into which the data values will fall, right? So we can pick different bends or intervals that we want. However, I'll pretty much always just give those to you when I'm asking you to draw a histogram. But if you pick, if you were to pick something different, the histogram would still be accurate, right? As long as you're doing the procedure correctly. So number 5, what we're doing is counting the number of data values in each bin and fill in the table, right? And since we're talking about grades, it makes sense for our data values to our class width to be 10, right? Alright, so if we just look back up at our original data set, you would just count. So there's one value, I believe, from 40 to 49, 0 and 50 to 59, 2 and 60 to 69, 6 numbers in 70 to 79, 3, 80 to 89, and 2 and 90 to 91, or 90 to 99. Right? So frequency is just the count, and then we can come down here and draw the bars. So 40 to 49, right, would be 1. So we would just draw 1. And you could shade this in. And then for 50 to 59, we have 0. but then 60 to 69 we have 2, right? So we would come over here to 2, draw a line, right? Shade this in, right? So you could use a ruler to be more accurate, right? I'm just eyeballing it here on the computer. So then 70 to 79 we want 6, right? So that would go all the way to the top. Right, so something like this. 80 to 89 we have 3, right? So we would match up 3. Looks to be about here. Remember the histogram, our bars are touching. And then 90 to 99 we want about 2. Right? So should have something like this, right? So then number 7 has a question. It says, why is the histogram referred to as a distribution of the data value, right? So the reason why it's referred to as a distribution is it shows how the values are distributed with respect to each other. Right? So that's why we refer to it as a distribution, because it can show how the values are distributed with respect to each other. So then, following along with that distribution idea, it says consider the following normal distribution, right? So this graph listed below, this is referred to as a normal distribution, right? and also it's also called a classic bell shape because it looks like a bell, right? So it's very important that that we understand that this is a histogram, right? But what we do is so there are still bars showing frequencies like going from here to here, right, and so forth. But if we keep so then there's more bars here, right, all the way, all touching. So if we keep letting these bars get smaller and smaller and smaller, we're going to get like this smooth shape, right? So if you imagine if you have bars that are really big and then you just keep getting it really small and then get even smaller, right? Eventually you're going to get like this smooth curve, right? So this is still a histogram, right? A distribution shape, right, as we looked at before previously, allows us to look at the overall shape, right? So remember we looked at a worksheet with like right skew, left skew, uniform distributions, and so forth. And I had a column showing possible histograms, what those might look like, and then what the overall shape looks like. All right, so this is a normal distribution, and so a sample will never be normally distributed, but what we can do is there are some statistical tests we can do to see what's the probability that this sample came from a population that was normally distributed, right? So there's some methodology that we can do, right? But we're not going to get into that. I will tell you, I'll tell you if something is normally distributed, right? But SAT and ACT scores is something that's known to be normally distributed, right? And also IQ scores. So in this table, what you want to pay attention to is if we look at this axis, right? These are the Z-scores, right? So if you remember, this symbol, right, theta, is used for the population standard deviation, right? So if I'm 1 theta away, right, 1 theta, this is a Z-score of 1, right? So this is a Z-score of 2, of 3, of 4, right? So these are my Z-scores. This will be a Z-score of 0, -1, -2, -3, and -4, right? So whatever's in front of theta, that's the Z-score, right? Another thing to notice is if we look at the data between here and here, this adds up to be about 68%, right? In fact, I was always taught the 68, 95, and 99.7 rule, right? So if you're within one standard deviation away from the mean, 68% of your data will be within that range, right? So that's in between -1z and 1z, right? One standard deviation away, so going both sides. If you're 2 standard deviations away, approximately 95% of your scores will be in between you're in between -2 and 2z, and then 99.7, so most of your z-scores will be in between 3 standard deviations away, right? So in between -3 and 3, which is here, right? There's roughly 99.7% of my data in between those, right? And these numbers will be very close to this, right? And notice also our diagram is a little more accurate, and also in between 0 and 1 it's labeled, right? So remember, it's symmetric. So the area under the curve between -1 and 0 has to be the same as between 0 and 1, right? Notice how those values are the same. So in between -2 and -1 is the same as between 1 and 2, right? Because it's symmetric. All right. Good. All right, so let's look at number 8. So it says, what percentage of people will have an IQ score that is more than 1 standard deviation above the mean, right? So one thing that I want to mention really quick. So underneath this underneath this curve, there is of course 100% of our data, right? So in other words, this has a value of 1 underneath, right? So if we're asked what percentage of people have an IQ score that is more than 1 standard deviation, right? So let me do some erasing so it's a little clearer. All right. So let me grab a highlighter. So we want to know percentage of people that is more than 1 standard deviation, right? So we want to know all of these values, right? So to get this, we would just add up what's in the yellow. So we would take 13.59% plus 2.14% plus 0.13%. Right, and if we add those all up, we get 15.86%. Right, so we assume that 15.86% of scores will be in this range, right? So higher than 1 standard deviation. And the last question says, notice that the normal distribution has less than 1% of the data values outside of 3 standard deviations from the mean. What is the IQ score of someone with a z-score of 3, where 3 or higher is considered genius? What is the SAT score of someone with a z-score of 3, right? So in order to compute those, right, we'd have to use the equations from above, right, from number 4, right? So for IQ, right, we want to know the IQ. So this was 100 plus 15 times 3, right? This would be of 145, right? For SAT, this would be 500 plus 100 times 3, which would be 800, right? So these are the scores you'd have to get to be to have a z-score of 3 away, right? Alright, so that's the end of that worksheet. I'll see you guys later.